Hello students, today we are starting a new chapter which is called as Equilibrium. It is the last chapter in the first textbook. So in this video we are going to introduce the term equilibrium and its type. As in the liquid state, we are already come up with this word equilibrium. So just recall the equilibrium as we have learned in the vapor pressure. In this, we have learned that when a liquid is placed in a closed container, when it forms a vapors, so these vapors will exert a pressure on the wall, that is vapor pressure. Here, the molecules in the liquid phase continuously vaporizes and simultaneously a stage is reached where the molecules in the vapor state that get condenses. So a stage is reached where the rate of evaporation is equal to the rate of condensation. That is, rate of evaporation is equal to rate of condensation. That stage is actually called as a equilibrium stage. So we have come up with the word equilibrium. So let us discuss more about equilibrium. So let us make a plot between the concentration of reactant and product versus time. So let us discuss this plot. For example, a reaction, consider it, in which the reactant is converted into product. So at the beginning, we can say that there is only reactant, no product. Here the reactant I am representing in R and product I am representing in P. So at the beginning, that is when the time is 0, at the beginning we can say that there is only reactant, because here the product you can say it is 0, because at the beginning before the reaction is starting only reactant is present, no product. But as the times moves, we can say that when the reaction begins, the concentration of a reactant goes on decreasing. That is, you can see the plot is go on down. It moves in the down because the concentration of reactant is decreasing. But as the reactant is decreasing, the product concentration is increasing. That means you can see the plot for product that is increasing. So a stage is reached where we can find out there is no change in the concentration of reactant and the concentration of product. That means here a stage is reached where the concentration of product is not changing as well as the concentration of reactant is not changing. That stage we can identify here in the plot in the straight line. So here is a straight line, here is a straight line. So that shows that it is a stage where the concentration of reactant is not changing, because when you look at here, the value of concentration of reactant is as it is and what the concentration of product is as it is. So that means in this stage we can say that the concentration of reactant is not changing and the concentration of product is not changing. That is clear from this plot that the value is not changing. So this stage is actually called as water, that is equilibrium stage. So how you define an equilibrium stage here? The equilibrium is the state at which the concentration of reactant and the product do not change with the time. So that stage is called as equilibrium stage. Now why it happens, why there is no change in the concentration of reactant and product at this stage? Because here the rate of forward reaction is equal to rate of backward reaction. That means the reaction is taking place in both the direction. That means reactant is converted into the product as well as the same amount or same concentration of product is converted into the reactant. So here both the process, that is forward reaction. This is called as forward reaction, and this one is called as backward reaction. So both the reaction is taking place in the same rate. Therefore, we can say that there is no change in the concentration of product as well as concentration of reactant. Now, let us discuss the types of equilibrium. First, the equilibrium in the physical process. The most familiar examples are the phase transformation processes. That is, example, solid converted into liquid, liquid to solid. So here the two double-headed arrows, that is two arrows which is showing here, that shows that the process is taking place in both the direction. That is it's showing the equilibrium condition. The two arrows in the opposite direction shows that the equilibrium condition or the equilibrium stage it is showing, where the process is taking place in both the direction. So solid liquid equilibrium, then we have liquid gas equilibrium, then solid gas equilibrium. So let us discuss these equilibrium in detail. First, solid liquid equilibrium. In order to explain these equilibrium, consider a solid, that is ice, kept in a water. So here the two state is the solid state, that is ice, is kept in water, that is in the liquid state. At the temperature 273 Kelvin atmospheric pressure, the solid is kept in the liquid. It is in the insulated thermos flask. So at the time we can find it out after some time. We'll see that there is no change in the amount of ice and there is no change in the quantity of water. So at this stage we can say that it is an equilibrium stage between the solid water and the liquid water. That means here the two processes is taking place in the same rate. That is the rate of melting, that is the conversion of converting the solid into the liquid. That process is called as melting. So the rate of melting is actually here is equal to the rate of freezing. Freezing is the conversion of liquid into solid. So here both the process is taking place in the same rate. That means how much of solid is melted, in the same rate that much of liquid get freezed. So we can say that there is no net effect in the change in the quantity of ice and the water. That is at the temperature 273 Kelvin and at the atmospheric pressure. So, for any pure substance at atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium are called as normal melting point or normal freezing point of that substance. So, this is what actually in the case of equilibrium between the solid and liquid, so the dynamic equilibrium is formed here. So the system here is in dynamic equilibrium and we can infer the following here. That is, both the opposing process occurs simultaneously. Which are the two opposing processes taking place? That is, melting and freezing is taking place. So both the processes taking place here simultaneously and both the processes occur at the same rate, so that the amount of ice and water remains constant. So we can say that because of here there is an equilibrium between the solid phase and the liquid phase of water, as here the melting and freezing process, both opposing process takes place together at the same rate. So we can say that the amount of ice and the water remains constant. So this is an example of solid liquid equilibrium. Let us discuss liquid vapor equilibrium, as we have already discussed liquid vapor equilibrium in the chapter states of matter when we have discussed about liquid state. That is, when the water is taken in a closed container, when it undergoes evaporation. So two layers which is formed here, that is liquid layer and the vapor zones are formed. So here a stage is reached when there is no change in the quantity of water and the number of molecules of vapors will be same. At this stage we can say that the water in the liquid state is in equilibrium with the water in the vapor state. So here it is taking place in this way because the rate of vaporization is equal to rate of condensation here. That means the two opposite process. Evaporation, that is a conversion of liquid state into vapor, and condensation, that is conversion of vapor into the liquid state. So the two opposing process which is taking place together here and at the same rate, that is, we can say that because of this reason there is no change in the quantity of water as well as no change in the number of molecules in the vapor state. So this stage is nothing but called as equilibrium stage. Next one, that is solid vapor equilibrium. Let us consider a system where the solid sublimate to vapor phase. For example, iodine. Iodine is a solid which can vaporize directly into the vapor state without being converted into the liquid state. So if we place a solid iodine in a closed vessel, after some time the vessel gets filled up with violet vapors. As you can see in this picture, the glass vessel is filled with vapors that is violet in color. As the time passes, the intensity of this color increases. But after some time, the intensity of the color becomes constant. That means up to a certain time only this coloration increases. But after some time, there will be no changes in the color. That means the coloration will be as it is. That means the intensity of color become constant. We can say that at this stage, we can say equilibrium is attained. Hence, here, at this stage, the solid iodine sublimates to give iodine vapor, and at the same time, the vapors condenses back to form solid iodine. The equilibrium can be represented as I2 solid, which is converted into I2 gas, and again I2 gas is converted into I2 solid. The other examples showing this kind of equilibrium are, that is camphor solid into camphor vapors, ammonium chloride solid into ammonium chloride vapors. So in these stages, solid phase is converted into the vapor phase directly. That process is called as sublimation. So this is what actually the equilibrium between the solid vapors. Next one is the equilibrium involving dissolution of solid in liquids. The process of dissolving solids in liquid is called as dissolution. So let us see the equilibrium involving during the dissolution of solids in liquids. We know from our experience that we can dissolve sugar in water. That means when we add sugar in the water, it gets dissolved, but only the limited quantity of sugar or the salt in a given amount of water at room temperature can be dissolved. A stage reaches where no further dissolution can be possible. So that type of solution in which no further dissolution takes place at a particular temperature, that is called as a saturated solution. So in a saturated solution, we can say that a dynamic equilibrium exists between the solute molecules, that is in the solid state, and in the solution, which can be represented as sugars in the solution form is in equilibrium with the sugar in the solid form. So this equilibrium is due to the rate of dissolution is equal to rate of crystallization. It means that during the dissolution process, a stage reaches where there is no further dissolution takes place. That means the further solid will not get dissolved, but actually the solids are dissolving at the same rate the already dissolved solid, that is in the solution, it get crystallized, that is to form crystals of sugar back. So the two processes taking place at the same rate, and both the processes are opposite. So here we can say that the equilibrium stage is attained. In the case of solute like salts, we can explain this in this way, that is, in the first stage only dissociation of the ions is taking place. That means only process occurring is the dissolving of the salt. That means only the process first in the beginning, that is dissolving, takes place. That means the solution is only in the solution, that means the solute is only dissolving. As soon as the ions floating in the water begins to collide and the salt crystals are pulled back into the salt, that means after some time the precipitation, or we can say the crystallization, begins. So the already dissolved salt or the sugar is present, they start to crystallize. So the opposite process begins, and evenly the rate of dissociation is equal to the rate of precipitation. That means the rate of dissolution is equal to the rate of crystallization takes place. Now the solution is called as saturated, because at this rate we can say that the equilibrium is attained. So here is the equilibrium between the solid and liquid during the dissolution process. Next, equilibrium involving the dissolution of gases in liquids. Do you know that the gases can also be made soluble in liquid as like solids? But that is in the high pressure. Let us take one example. In the coke, that is the carbon dioxide is made to dissolve in the liquid, that is in a high pressure. So when a soda water or the coke, when it is open, it gives a fizz sound. That is familiar to you. This is because the phenomena, that is the difference in the solubility of carbon dioxide at different pressure. As the pressure inside the bottle is high, so at high pressure the gases is made to be dissolved in the liquid. But when we open that lid, the pressure get reduced. So because of the reduce in the pressure, the solubility of that gas decreases. So it comes out with a fizz sound. At high pressure, the carbon dioxide is made to dissolve in the liquid. So here these are in the equilibrium condition, that is the carbon dioxide aqueous and the carbon dioxide gases is in equilibrium condition, which is represented here, that is carbon dioxide gas and carbon dioxide in the solution is in the equilibrium stage. So this equilibrium is governed by Henry's law, which is important here. It states that the mass of the gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above that solvent. That means here the solubility of the gas depends upon the pressure. So the mass of the gas dissolved in a given mass of a solvent, that depends upon the pressure. So greater the pressure applied, greater mass of the gases can be dissolved in the given mass of solvent. So we can say that according to Henry's law, the pressure we are applying that is directly proportional to the mass of the gas which get dissolved in a given mass of a solvent at any temperature. So the pressure plays a very important role in the solubility of the gases in the liquids. Now let us see some important points related to this, that is the process and the conclusion. In the liquid vapor equilibrium, that is water, liquid to water gases, the important conclusion is that pH2O is constant at a given temperature. Here the pressure of that water is constant at a given temperature. But in the case of solid liquid equilibrium, melting point is fixed at a constant pressure. Here melting point is fixed at a constant pressure. But in the case of solute to solvent equilibrium, that is sugar solid to sugar solution example, the concentration of solute in the solution is constant at a given temperature. Last one, that is the carbon dioxide gases with the equilibrium with the carbon dioxide aqueous. In this condition, the gas in the aqueous state, its concentration by the gases in the gaseous state is constant at a given temperature. So these are the important conclusions related to the equilibrium in the physical state. As we have learned the physical state equilibrium, that is liquid vapor equilibrium, solid liquid equilibrium, then solute solution equilibrium, gases state to gases aqueous state equilibrium. So these are the important equilibrium, that is the physical equilibrium we have discussed. So this is all about this video. Have a nice day.